All right, so it's now time to do a combined example where we're going to be, any one of us here is going to be given a graph that represents a function. And from that graph, through that graph, we are going to find and identify the domain and the range, okay, of the function that's given as a graph. Okay, so here's the wording description of the example. And let's now call that example 3 in continuation to the earlier examples we have seen. Okay, so here I would say find the domain. Okay, find the domain and range. Okay, so we're finding two things in each of our graph right here, and of course express these in interval notation. All right, so find the domain and range in interval notation of the function represented by the following graph. All right, so now once again we're going to walk through about a couple of problems right here where each one of these problems is going to have a graph right from the beginning. And we are going to identify using our experience we have seen up to this point. So we're going to find and we're going to identify, or we're going to find the domain and the range, okay, from the given graph. All right, so now it comes part A. Okay, so now allow me to show the graph. And again, I'm not going to show a hand sketch version, but instead I'm going to show the version that from the computer screen. I'm going to bring it right on screen right here. All right, so now here we go. This is the first graph. All right, so in part A, we have the graph as seen here right now. And so now let me bring that into full screen view right here, okay? And I am going to zoom it in a little bit, okay, to make it easier to identify, to see the grids and the numerical labels on the axes right here. All right, so now let's find the domain and the range of this graph right here. So now learning with through the examples we have seen earlier, then to find the domain, and domain is always the first thing to find. Okay, for a problem like this, it's intended to, this problem is brought up in the intention that a lot of times you will be asked to do two things. So domain is always the first thing that we need to identify right here. Okay, so among the two things here, finding the domain and the range of any of your given function. Domain is the first thing to find. So now right here from that given graph right there. And now again, I'm going to switch to full view mode right here. Let's look at, I'm going to place in a vertical line. So the vertical line is just, at least to me, it's a very effective tool that I'm using to identify my domain right here when a graph is given. So again, just like earlier examples, now anywhere currently that I'm putting currently at any place that I'm putting my vertical line right now, there's no cross. There's no place and there's nowhere here that's crossing, that the vertical line is crossing with the graph. But now anywhere in between about, so the grid is telling the story anywhere between -2 and 8 right here. Okay, so if I put my vertical line in between -2 and 8, then the vertical line will cross the graph at some point. All right, so in that way, now clearly we can see that as far as the domain, all right, the domain happens anywhere, well, the graph is defined anywhere between -2 and 8. So we already found an interval. But now let's carefully consider, let's carefully explore the end of the two endpoints of the domain right here, whether we including any of one of the endpoints or we just having that as an open interval only. Okay, and so if we're looking back again at this current graph right here, then on the left end right here, on the left end we had a solid point. We have a solid point, and now let me again bring it in the full view, full screen mode right here. So this solid point right here is indicating that when x equals -2 specifically, we do have a point on the graph. Okay, we do have a point on the graph, and so obviously this line does go through this vertical line does cross the graph at that particular point, and that's why we have a solid point right there. And so now in that way, I'm saying that on the -2 end right here, the left end of our interval, it's a closed brackets there, it's a square brackets there. Okay, so what about on the 8, on the right end of our interval? All right, so now I'm going to move my vertical line to the right end, and let's see what's happening right at the right end. And so with that, and now again, I'm going to bring that into full screen view right here, but now we notice there's an open point right there. Okay, so that open point is indicating that when x equals specifically 8, there's no point, there's no value, there's no height defined, and there's no height defined on this function. That's the way how this function is indicating. Okay, so that means anywhere else strictly less than 8, or graphically speaking, anywhere slightly to the left of 8, okay, even a tiny bit like that, is still going to have a point specifically crossing through the graph. But now when it's equal 8, when it's equal 8 precisely, okay, when it's equals 8 precisely, then there's just no height right there. Okay, so that means x equals 8 is not included. All right, so now that we complete our interval that indicates the domain of the function. All right, so now on the same graph, let's now look at the range right here. So now I'm gonna hunt for the range. All right, so now the range is now on the graph. I'm gonna hide away my vertical line, but instead I'm gonna use a horizontal line to identify the range right here. And so remember, the explanation I've been giving is that the range is the vertical spread of your graph. And so now that's why it's now intuitive that we're using a horizontal line. The horizontal line, and we bringing it up and down to see where the horizontal line will cross anywhere, to recognize, to spot anywhere the horizontal line will cross with the graphs. All right, so I'm going to be bringing my horizontal line up and down. Okay, so we can see that, oops, anywhere above that, about above this height 2 right here, then the horizontal line I'm using here is not crossing the graph at all. Okay, and anywhere between 2 and, let's see what that low is, about -1. Okay, so anywhere between -1 and 2 vertically on the vertical scale, that's where, and again, let me bring it into a full screen mode right here. Okay, so anywhere between -1 and 2, that in that vertical interval, that's where we recognize that our line will cross with the graph. Okay, so apparently the range here has to produce outputs, the function produce outputs that's falling in anywhere inside of, in between -1 and 2. So we have an interval already, and now let's find out if it's what's the end behavior, what's the behavior on these two ends right here. Are we including the endpoints, or excluding the endpoints, or only including one of the two endpoints? That's the idea. All right, so now back in this problem right here, and again, let me put that in full screen view right here. So as far as the low, we do reach down to as low as y equals -1, and when y equals -1, the graph is telling me that when x equals 3, we do have a value here. So when x equals 3, we hit down to y equals -1. So that means for as far as the bottom, we do come down to as low as -1. So now I'm including -1 as the low. Okay, so what about the upper end right here of our interval? Let's see, are we including that height? Are we including that height or not? Okay, so what matters is whether the graph, the horizontal line, will cross the graph at that particular height. So I'm going to bring the horizontal line up to that height right there. All right, so in full screen view of our graph right here. All right, I'm going to bring it up. I'm going to keep bringing it up, and right there, when this line, this horizontal line is seated at y equals 2, we do have a value. We do have a y value equals 2 on the graph. On the graph, we do have a y value equals 2. So in that way, now it's clear to make that conclusion. Okay, so the range for this function here, according to the way how it's written, the range now is anywhere from -1 to 2, right there, inclusively. Okay, so that's how we found the domain and range of a function, of our function here, but given, represented as a graph, through a graph. All right, so now I am going to clear out the board, and let's make space for part B, where I'm going to show another graph. All right, so here we go. Let's look at part B right here. So the graph for part B is the following. All right, so this is the graph for part B. So feel free to copy and paste this into your notes in case you're taking notes and studying along with my video lesson right here. Okay, so here's the graph for part B. We want to find the domain and the range and express the final answer in interval notations. Okay, and then the function is given as a graph right here. All right, and so now let's get into it. I am going to bring that into full screen view right now. So again, just as an effective tool that has been working really well for me, I am going to throw in my vertical line to detect where the domain is. Okay, so as far as the vertical line, here's my vertical line. Anywhere right now that where I'm currently putting the line, it's not crossing with the graph in red at all. Okay, that's what, and now I'm going to horizontally moving it. I'm going to move this vertical line sideways to the left hand side slowly, and it's still not crossing with the graph yet, but now we start recognizing there's some crossing. Okay, so what happens now is that what I see now is that anywhere between -2, anywhere between -3 and 2. Okay, I said a little bit incorrectly earlier, but anywhere between -3 and 2. Okay, that's gonna have, we're gonna have our domain happening anywhere inside of that interval. Okay, and so in that way, here comes our writing. Okay, so for domain, anywhere between -3 and 2. So strictly, for sure, or surely anywhere between -3 and 2. The vertical line is crossing with the graph. Okay, but now let's consider the two endpoints here. What about the endpoints? Are we including those two or excluding those two, or are we only taking one of the two endpoints right there? Okay, so in that way, let's have a look at the graph a little in a closer view right here. Okay, and so now I'm going to bring my vertical line to the left end right here, and right at x equals -3. Okay, right at x equals -3, and now momentarily let me hide away my vertical line, but we have an empty point right there. That means when x equals -3, or right at this vertical line, we don't have a value, we don't have an output defined for that. So that's what the meaning of this empty point again. And so in that way, now I'm saying that I'm not including -3. Okay, so at this point now, anytime we see an empty point on the graph, it means we're not including that endpoint. Okay, what about a 2 right here? And so now on the graph, moving the vertical line over to x equals 2. Okay, we have a solid point. So this solid point now in our experience, it means we are including x equals 2. And so that completes our interval of the domain right here. Okay, and now let's look at the range. All right, and so now for the range. So for the range, I am now going to hide away my vertical line, but instead I'm putting in my horizontal line. All right, and then we're going to move the horizontal line up and down, okay, to detect places or positions where to detect which interval where the line is going to cross with the graph. Okay, so right now where I'm putting it, the horizontal line in dotted line right there is crossing with the graph right there. And then I'm gonna slowly moving it up and down, so it's still crossing, and here it's no longer crossing. And then there's a certain bottom low that after going lower than that, it's not crossing any longer. And so now apparently my dotted line is crossing through the graph anywhere between -5 and 4. So let me now bring it into closer view right here. So anywhere between -5 and 4, my horizontal line is crossing through the graph at least once, or one time or 2 times. Yeah. Okay, once or twice. See, this is twice at some other places. Okay, the line is only crossing with the graph once, but then in the end, in between the vertical coordinates, in between the vertical values from -5 to 4, then this horizontal line of mine is crossing with the graph. All right, so in that way, the range must be happening anywhere between -5 and 4. All right, and so now let's find out whether we are going to include the two endpoints or excluding the two endpoints or just only taking one of the two. Okay, so in a closer view right here again, when it comes down to y equals -5, there was no x value for that. Okay, or in other words, empty point right there. Okay, empty point, but vertically down here we have an empty point. So there's no x value that satisfies this height being -5 right there. So in that way, I'm saying that we're not including -5, okay, in our interval. Okay, so just vertically, there's no y equals -5. There's no y equals -5 as the outputs. Okay, and then there's a solid point on the graph. Actually, it's not clearly shown as a solid point actually, but it's up here. Okay, it's up here, and in a closer zoom right here, see, when it gets to that height being y equals 4, we do have a value x equals 0 that leads to that height, that leads to producing that height y equals 4. Okay. All right. So now when I have y equals 4, the graph in red here does hit to that height due to the fact that when x equals 0, it's estimated that the height is 4. So in that way, now the range here, as far as the range vertically speaking, we do include y equals 4. So now that's the range, that completes the range of our graph right here for this whatever function that is. And throughout the entire examples, and all of these examples that have a graph given right here, then we never had to worry about determining the rule, the written rule that decides our function, that determines the output of our function. Okay, and so that completes our example 3 right there. And now I am going to bring up another example where we call that example 4. But we're going to specifically focus on finding domain and range. It's worth it, even though this kind of challenge, this kind of problem doesn't happen too often in your days of doing mathematics out there. But it will come back sometimes here and there. So it's worth a little bit. It's worth to spend a little bit of attention, to put a little bit of attention on this kind of problems in the following example I'm about to bring up right here. Okay, so let's look at example 4 here. We're still going to find a domain and range. Find a domain and range. Okay, find a domain and range of the function given as the table below. All right, so now we have a function here that says inputs. Let's stick with the tradition calling the input variables, the input values, the x variables. So I have 1, 2, 3, 4, and 5. Okay, so we have a function value here, a function with a field defined as a table, or it's already represented as a table. It has a rule that's not clearly written out, but at least we've seen the table representation of that function. And that's what it says right here. And so now function output here, let's say we're looking at 8, 7, 6, 7, 8 right there. Okay, and so now when we're in the situation where the function is defined as a table like this, so it has a rule. The table itself represents the rule. Okay, and we have seen this idea quite a few times before. So now in a case like this, to find a domain, okay, and I have brought up this little example earlier, a little example earlier when it was vending machines earlier. But now it's time to formalize that into an actual example. So now, when we're in a situation where we have a table like this, then well, ideally, or by default, we're looking for a domain expressed as an interval. But here, since the domain, recall in the end, the domain is just a set of possible input values to a function. Okay? And so a set, but now we only have a few limited number of values in that set. So only we have all of those values from 1 to 5 like that. And so in that case, and that's my intention, we just want to introduce the idea that sometimes when we can't use the interval notation because our set is discrete like this, okay, then we have to use we have to stick with the standard set notation right here. So 2 curly braces, and I'm listing the members of the set, the values inside of the set between my 2 curly braces, and that's my domain. It's the set of inputs that's possible for this function. Now see, why is it only these values? Because these are the only values where we know what the function gives outputs for. Okay, these are the only inputs, these are the only inputs that's possible for us to come out with an output. Because if we're asking for f of 7, if we're looking at 7 as the inputs, there's no definition. The rule doesn't have any definition saying what to come out for x equals 7. So in other words, this is undefined. So x equals 7 as an input is impossible. Recall that we talked about possible inputs or impossible inputs. So the only possible inputs, values for this function f of x are these members in this set only. And so that's the domain right here. But in some small percentage of time right there, right? In some small percentage of time right here, then we have to express domain or even later on the range in set notation. Okay? And so in that way now, range, again, ideally we're looking for expressing the range as an interval. And again, the definition of the range says it's the set of all possible outputs, values, okay? The set of all possible output values of a function. These are the only output values of a function. Now we have a few repeats here. The 7 is being repeated, the 8 is being repeated. So we don't need to count like this. 6, 7, 7, 8, 8. We don't need to count the repeats because in the end, having 2 8s, it's just the value 8 being present in that set of range. And then we don't have to count the repeat for 7. So now really the range is just 6, 7, and 8. Okay, those 3 values are the only possible output values to this function right there. Okay, and then we have to put these values in a set notation right there instead of an interval notation, because we don't have an output being 7.5. Okay. There's output equals 7.5 is not found. The function will not, according to this function, it will not produce any output. It's impossible for this function to produce any output being 7.5. And that's the idea right there. Okay, and so now that's how, and that's the end of this example 4. My only intention for that is that to give the viewers and students of mine to learn a little bit of experience. There will be times, a small amount of times out there only, but there will be times where we have to step out of the normal, of the ideal situation that we express domain and range in interval notations. But sometimes we need to be able to express the domain and range in set notations like this. Okay, and also it gives you the experience of reading domain and range from a table given. Okay, all right. All right, so now in the next class of problems, and tentatively I am going to produce a few more examples after example 4 over here. But the next class of problems here, I am particularly going to focus. And more importantly, we're going to focus on these kind of problems where we have a function given where the function is already having a written down rule. Like say for example, f of x equals 2x plus 1. Okay, what's the domain? Find the domain. So we have a rule specifically given. Okay, and then from that rule we we want to know from that given function. We want to know what the domain is. And then for the later examples, we're mostly going to focus more on the kind of problem where we only need to identify the domain, because finding the domain is a lot of times more important, okay, more priority, at higher priority than finding the range, okay. And so in that way, let me introduce a couple ideas right here before we get into doing any of these example problems like that. But for example, if we have a function f of x and with a specifically given rule right here, 3x minus 1. Okay, with a function like this, we have a rule. We know the rule is telling us explicitly what to do with the inputs here. Then so we can try a negative input, okay, and it gives me 3 times negative 1 minus 1. So I have to mention, according to the kind of operations, according to the way how this rule is set up, how this rule is defined, the way how the operations being involved in this, in this rule is, okay, according to that way, then there's nothing wrong with taking an input. So here I'm using an input negative 1 here, and I said maybe I missed some little information, but what I meant earlier is there's nothing wrong with taking a negative input. So here I used a negative 1, but you should see this a quick little problem as something that represents a more generalized case, that if we put in a negative input, what's going to happen? Nothing bad. Nothing critically bad about this. 3 times the negative input, which is entirely possible for us. Okay, gives me a negative 3 minus negative 1. Nothing impossible in this next step. And so we come out successfully with an output being negative 4. So substituting in a negative value gives us an output just fine. So we had our function outputs value defined at this negative input, and generally for any other negative input. What about when we substitute in a 0? Okay, and so 3 times 0 minus 1 according to the rule of this function. The operation between 3 and 0 is a multiplication. 3 times 0. There's nothing critically wrong about that. We know how to multiply 3 with a 0, any number with a 0. So we have 0 minus 1. Nothing's wrong, nothing critically wrong about subtracting a 1 from 0. So we have an output being negative 1. So in other words, when we use input specifically equals 0 for a function like this, okay, then we have an output successfully calculated. Okay, so what I'm trying to say now is that for some function in the way it is, there's nothing critical with any inputs. So we have tried negative inputs, 0 inputs. What about a positive input? Say, let's put in a 5 right there. So here I'm using a positive 5, but generally I want anyone viewing from this lesson to see this as generally, if we use any positive value for the inputs, then we're looking at 3 times 5, just the ordinary, just the usual multiplication, minus 1. So 3 times 5 is a 15 minus 1. That gives us a successful output that we can compute. So nothing's wrong there's nothing bad about using or substituting a negative input into this function, into this rule. There's nothing bad about substituting an input 0 into this function, because the rule is only involving multiplication and subtraction, or multiplication and adding sometimes, and addition sometimes. And then the same with positive inputs. Nothing's wrong with an operation like this. Okay, so now, in other words, with a function like this, where it only involves just the basic multiplication, maybe with some high rise power, okay, and then the addition and subtraction, then the domain for this function is anywhere from negative infinity to infinity. All real values. Okay, and that's my point. So outside of this function, you see x squared, you may see the power functions and all that. The domain for those functions should be just anywhere from negative infinity to infinity. Okay, so this one kind of function is pretty easy on the domain. It takes all inputs, all numerical input values. Okay, But now let's look at some other functions. The kind of function that mainly needs, at our level right now, the kind of function that mainly needs our attention a little more closely is the following. Let's look at, how about I'm going to give the function as following. And we have seen this function quite a few times up to this lecture right here. Okay, and I also use this as one of those problems among the earlier examples right here. So, clearly speaking, this function has domain in interval notation. In interval notation, negative infinity to 0, and from 0 to positive infinity, okay, and with a union. But the whole idea that led to this, conclusion about the domain is that simply for this problem, for this function, 1 over x, f of x equals 1 over x. The logical reasoning that led to this conclusion, recall from earlier examples, that it's simply because x inputs, the inputs, just cannot be equal to 0 for this function. I made that argument earlier in the earlier examples. It's undefined. See, in other words, f of 0 is undefined. And we have seen this even much earlier. Okay, we don't have an output value defined for this. So now, for this specific function, 1 over x, okay, we cannot take input x equals 0. And that's the only input that we have to rule it out. And that's why the domain is broken down into two separate intervals. One of them is between negative infinity and 0, and the other one is between 0 and positive infinity. But we just won't take x equals 0. I keep emphasizing that. Okay, but now let's even push that a little forward, right, and to have a broader understanding, a little bit more, a more generalized understanding. Now, the aim is not to only keep repeating, hey, your x has to be non-zero here for this function, x has to be non-zero here for this function. Yes, anybody knows that at this point. My point now is that I want you to see that the point now is that anytime we have a denominator, so right now the denominator is only one single variable. And that's why the value for x singularly must be non-zero. Okay? But now I'm talking about what if the function here comes as the following, like a 3 over x minus 4. Okay? It's not simply just an over x, but it has something common. This function I just now brought up on my Scratch workspace right here. This function has something in common. With this function 1 over x right here, it has a denominator. Okay, and so now allow me to go in slow steps right here. So from this function 1 over x, we ruled out x equals 1. So x must be anywhere not 0. We ruled out x equals 0. That's what I meant to say earlier. So x must be non-zero. X must be other than 0. But now, more generally, from this, we have a further understanding that it really means that the entire denominator. See, so now the denominator here is not only an x, it's like the whole x minus 4. So we basically want the whole x minus 4 must be non-zero. We want the whole x minus 4 to be non-zero. That's something to keep in mind. Or even more generally, anytime we have an expression, okay, a over an expression, we have a rational expression like that, and a over some expression, then we need the denominator, because this expression stays in the denominator. We need the entire expression must be non-zero. Okay, so that's one thing. So now after getting this, nailing down this generality right here, let's set to that into some example right here, and we will dive in a little more. All right, so now let's call that example 5 right here. Okay? And here we just want to find the domain. And of course, now the default is to the default is to express the final domain in interval notation. Okay, so find the domain of the following function. All right, so now part A. So let's look at f of x equals 9 over x minus 6. Okay, 9 over x minus 6. I could have also used the earlier problem that I brought up like that. Okay, but so observation now is telling me that this function, well, it has a specifically written rule. Okay, and we want to find out, so in this rule how it is it has 9 divided by the entire expression here, see? So we have a value, or we have some expression divided by some expression, just like the general structure that I wrote down earlier, the general form I wrote down earlier. We have an expression, some expression in the denominator. So the entire denominator here is an x minus 6. Okay, so anytime we run into that situation, that kind of problem right there, then the first thing to keep in mind, we must always ensure that x minus 6 is non-zero. That's the idea. The logical reasoning is that we must always ensure the denominator is not equal to 0. That's what I meant to say earlier as well, in case I couldn't get straight to that point like that. Okay, we always need, anytime we have an expression that has some denominator, we always need to ensure that the entire denominator, it could be an x minus 6, or it could be like a whole, something else complicated, but we take the whole denominator, we want to ensure it's not equal to 0. And from there, it's going to start producing the work. We're going to start looking for the kind of work that's ensure. So how do we ensure x minus 6 in this case other than 0? So this is how we're doing it. So it's a little intuitive. And when classes are face-to-face, when I'm teaching a face-to-face class, I'm saying that the x values, this is what I'm starting out. I'm going to actually start setting out x equals 6. That denominator equals 0. Wait a minute. We want x minus 6 to be non-zero. Okay? But why am I looking for x minus 6 equals 0? Because here's the logic. Okay, so I'm calling that. This is bad. This is bad because x equals 6 is bad. But at least doing this, I'm going to find out precisely which value of x causes my denominator to equal 0. And I call that it's a bad guy. Okay? So x equals 6. So I'm going to purposely set x equals 6 equals 0. And I'm going to find out from this equation. Well, by the way, so far we have come up to an equation. So I'm going to purposely set the denominator equals 0. Okay, and to find out, to solve for x value, to identify, to find out who is the bad guy or who are the bad guys that causes x minus 6 equals 0. Okay, so in that way, algebraically, we're going to add 6 from both sides. Now, it's just for this equation, the way to solve for x. So that ends up with x equals 6. Okay, and so now here's the thing. This is the bad guy right here. This is the bad guy. So we searched and we found that bad guy, and that's the only bad guy. We have found that guy through solving this denominator equals 0. Okay, and so now solving this equation, solving that denominator equal to 0, we ended up with x equals 6 for the bad guy. So that means this function right here, now I need space, so I'm going to erase this. So x equals 6 is the bad guy, but now we want to ensure x is minus 6 other than 0. So that means x must be other than 6. That's the reasoning right there. Okay, again, simply because x minus 6, we purposely set it equal to 0, and then we led to finding out that x has to equal 6. That's the only value causing x minus 6 equals 0. But then from that, now we're going to exclude that out. We're going to take that out. Okay? And so now once we're clear that, hey, we have to take x equals 6 out, because when we're doing f of 6, okay, we have an undefined. See, clearly. We didn't even have to do this. Now I'm just demonstrating the idea right there. because f of 6 equals 9 over 6 minus 6, which is 9 over 0, undefined. Okay, and so in that way, now everyone hopefully is clear that why I was doing this, setting the denominator equals 0, and then solve for that, solve for x. And then the x that you have solved, or the x values that you have solved from that equation, now we're going to rule them out. We're going to take those out. And that's why here we need, at first, initially or originally as a plan, we need the entire denominator to be non-zero. And now, but that means, logically means that the input values x have to be other than 6 in this specific problem right now. Okay? So we slowly getting there. Now that means the domain is anywhere. The domain is going to be any other values except x equals 6. That's what it is. Okay? And so now once we have had that idea, once we have had that conclusion, now it's time to formalize our domain, but in interval notation. Let's write that in interval notation. So I highly recommend using the graph right here to have a clear direction into your interval notation. The whole line right here. 6 is anywhere on this line of real values. We take any values other than 6. So we just shading here because it's that's represent any value other than 6. And then any other values here other than 6. We're just not going to take 6. So I'm leaving an empty point right there. And so now with seeing that graph, coming to the domain is completely clear. Anywhere between infinity, negative infinity, and 6. That's one interval. This left side, this shaded area to the left of 6, that's what it is. And then we're also going to take the other one, anywhere between 6 and positive infinity. Okay, those two, and then we're going to take the union between those. We're going to take the union between those. That is now our formal domain expressed in where the final answer is expressed in interval notation. All right, and so that's the idea. So hopefully you start, drawing out some generality from this problem. And now let's move on to another problem to enhance your understanding. Okay. So now before I rush into another problem, how about let's do an FYT. Okay, so FYT, this term I picked that up from my own favorite professors back then when I was learning math myself, when I was a student on my way to become a math professor. So FYT here is for your own trying. Okay, so the whole idea of any of these, so throughout your time learning with me, there will be quite a few times you see an FYT that I'm putting right here in the video lecture. It means I am not going to show the careful step, but I'm going to leave the work for you to try. And then once you proceed with the video, you only see me writing down the final answer. Okay, and then it's you who need to show the work. Okay, and so for this FYT, so what about that earlier problem that I brought up? 4 over x minus 3. Okay, so let's find the domain of this function. All right, so go ahead and pause the video, okay, and find the domain, just like the steps I've done in part A earlier, okay, for this function. All right, so now the domain in interval notation should be just anywhere between negative infinity and 3, and then anywhere from positive 3, between positive 3 and positive infinity, okay, and then union, and that's the final answer. And again, since this is an FYT right there, allow me not to show the actual reasoning work for that, because it works just like how we did that in part A earlier. Okay, and so now I am going to erase this, and let's step into another problem where I call part B of the current example. All right, so in part B, let's look at the following function. How about f of x equals, and now I'm looking at x minus 8 over x squared plus 8x minus 9. Okay, x squared plus 8x minus 9. All right, so for sure this function here looks a lot more complicated than the earlier one that you have done in your FYT problem, or in part A that I went over the steps with anyone viewing the video. This function does look a lot more complicated. But the idea now is but what's still in common? What's still common with the earlier problem is that it has a denominator. This entire part is the denominator. Okay, so keep that logic I pointed out earlier. What we need to ensure anytime we have an expression, a function, a rule that involves a denominator, that has a denominator, then we need to ensure. Okay, I wrote need earlier, but now how about we just need to ensure. This is always what we need to ensure. We need to ensure the denominator, the entire denominator, x squared plus 8x minus 9, be non-zero. That's what we need to ensure. That's our goal right there. And because of that, because of what we need to ensure, we need to first track down which x value. We need to find out what x values causing this denominator, x squared plus 8x minus 9 to equal 0. See, because it's all due to the fact that we need to ensure that the entire denominator being non-zero. So now we're going to start searching for them. In that case, see, to ensure a safe and sound and good community, what do we need to do? Search for the bad guys. Okay, so to ensure the whole denominator to be non-zero, non-equal 0, like that. Then what do? We search for all the x values that cause this denominator to equal 0. So I call all of those x value or values the bad guys. Let's search for the bad guys. And what do? Once we have found the bad guys? We rule them out from the community. We will rule them out from the domain. And that's the idea right there. All right, so now once we set up this equation and about to attempt solving it, then we realize it's just a quadratic. You take your choice, you take your own favorite method to solve, because at this point when you're learning this video lesson, solving a quadratic equation is on your own choice like that. Okay, you can go with factoring, you can go with the quadratic formula, you can go with complete the squares. It's pretty much your choice like that. Okay, I prefer, it's just for my own personal favorites like that. Okay, I prefer the factoring method because here it's easy enough to factor it. I'm not saying that I will always stick with factoring. There will be times I'll use the quadratic, which takes a little more time but always guarantee an answer. But here I see that we can go x minus 1 times x plus 9. Factor into. So that's quadratic. It's factor into 2 factors like this. And so now we're leading to x equals 1 and x equals negative 9. So let's understand the logic of solving this kind of equation a little bit. The real logical meaning is that when we come to solving this and finish coming down to this, it means either x equals 1 or x equals negative 9 will cause x squared plus 8x minus 9 equals 0. Okay, now hopefully you hear my word spelling out loud again. Either x equals 1 or x equals negative 9 will cause the entire denominator x squared plus 8x minus 9 equals 0. Either one of these. That means now, so that's the logic about solving. We found the two bad guys here. Either one of these two bad guys is going to be bad for the community, for the denominator. Either one of these two bad guys will be bad for this denominator. Bad in the sense that any one of these guys makes the denominator equal 0. Okay? But now from that understanding, then what do we want to do? We want to rule them out. So if we rule them out, we have to rule all of them. We have, see, when it's causing trouble, then any one of these guys can cause trouble. But when we take them out of the community, when we take them out of the domain, we have to take all of them out. We have to take all of them out. Okay, so in that way, so now I lead to the understanding that, so that means x must be on one hand not equal to 1. That's what we need. We need to ensure x is not equal to 1 and x is not equal to negative 9. That's what we need to ensure. Okay, so now once we have that idea in mind, this is already close enough conclusion. We already have a nice clear conclusion for our domain right here. It's just not the final answer yet, that's all. But so now let's put it on the graph right here. The graph, the line of all real numbers. Okay, negative 9 somewhere out here. 1 is somewhere to the right hand side. How far spacing between them, it shouldn't matter. So we take anybody else. We take anybody else except these two bad guys. That's the idea. So anywhere between, that works. Anywhere to the left of negative 9, those values work. Anywhere to the right hand side of 1, those values work. But just not at 1 and not at -9, we take those guys out. We have to take those two bad guys out. So in that way, now we got 3 separate intervals. Now we are ready for writing it. One interval is between -infinity and -9. That's one interval. And of course, we don't include -9, so it makes perfect sense to use the parentheses. We will take all values between -9 and 1. And again, open parentheses. I'm using round parentheses here because we're in this interval. We're not including any one of these two, -9 and 1. And then we go between 1 and positive infinity. Okay, and now we take a union. Ladies and gentlemen, this is your domain here. Expressed. I mean, this is the logical understanding of the domain. Okay? This is a graphical representation, and the formal final answer is expected to be written in interval notation. All right, but either one of these, any one of these is already, a clear indication of the domain already. But now in these modern days, a lot of instructors, a lot of professors expect their students to write domain in interval notation. That's what it is. All right, so we have 3 separate intervals. And then we're excluding -9 and 1 for this problem. All right, and so that's the idea about the idea about how we find the domain. And see, throughout the entire example here, I only focus on finding domain. We didn't have to worry as much about the range. Okay, and so now let's step into another example problem. We're now done with example 5. And allow me to leave the instruction, the wording there. So along this way, now allow me to point out another class of function here. And don't worry about, because I just don't want to rewrite that same wording for the next example, so I'm going to leave that here for now. But let's just look at this following function. Or maybe I'm going to switch to the other board and do some quick scratch work right there. All right, so I brought up this function as well. It's one function among our toolkit functions. So with this functions, we have learned earlier that the domain, as the final answer, we have seen the final answer about the domain of this function. It has to be anywhere from 0 and up. So from anywhere from 0 to positive infinity. That's the domain, and we were including 0 for this. All right, and then so if we backtracking the work a little bit, if we backtracking the reasoning, how we led to this conclusion, then the idea now is that it was a square root, the rule for this function. So again, we are now particularly focusing on those functions where we have a rule specifically given. Okay, and then from the rule right there, we're gonna find we're gonna just simply find the domain from the rules right there. Okay, and so now for this here, the rule is simply involving a square root. The rule is simply involving a square root. And so the reason we came to this final domain right here is simply because we need to ensure, okay? What we did earlier is that we needed to ensure that x is greater than or equal to 0. Because we could not take square root of a negative value for this particular function. F of 0, yes, we will have a defined answer. It equals to square root of 0. The way how this square root operation works for a human on Earth is that that gives a 0. Square root of a 0 is 0. It works just fine for square roots for the humans on Earth. Okay? Square root of a positive input. Now I'm using positive 1 here particularly, but I hope you're going to start drawing out that generality that generally when you use any positive inputs, it is entirely possible to find. So this input is a positive and it's a possible input for a square root operation. And so on. We have a defined output. But now if I'm using a negative input, I'm using -1 right here. But let's have that, let's draw out that generality from this right here. Generally at any other negative inputs, we're going to have to encounter square root of a negative 1. Okay, and without talking about imaginary number or complex numbers, then we don't know, we don't have an answer for this. Square root in the real numbers do not have an answer for square root of negative values. So we can't take square root of a negative value. So here, in other words, the answer is undefined. Okay, and so that's the reason why, and for this particular square root function, the reason we came to that domain is simply because we needed to ensure x, okay, is greater than or equal to 0. The input is greater than or equal to 0. All right, but now as a further impact drawn out from this particular function, then here's the idea. We will see a lot of times we will see function that involves square roots, but sadly but unfortunately the part inside the square root is not as simple as this. And that's the reason why when I was introducing this function as a toolkit function, I keep saying that it's a simple square root, because there will be other square roots out there. There will be other square root functions out there. Say, for example, a 3 minus x inside the square root. It's not as simple as square root of x anymore. It's, rather than being an x, here it's 3 minus x, an expression inside the square root. Or generally a square root of some expression. Square root of some expression. Okay, so when we run into that situation, similarly here, then drawing out a generality from this problem right here, then here's what we need. Anytime we have a function that involves a square root, anytime our function has a square root operation, we just need to ensure, okay, we just need to ensure the expression, okay, is greater than or equal to 0. Now this expression here, I mean whatever expression. It could be a 3 minus x, or it could be even more complicated expression, but we just need to ensure that expression greater than or equal to 0. We just need to ensure that expression to be greater than or equal to 0. Okay, and so now after we take that generality, let's get back to the other board and start firing up our next example right there. And we call that example 6, and where we're going to start diving in further. Here, the only fundamental I want to show, I want to make sure anybody to understand. Anytime we have a square root involved in our function, we need to ensure that the expression inside the square root, the entire expression inside the square root, to be greater than or equal to 0. All right, so now let's call that example 6 right here. All right, so in this example 6, we are going to do the exact same thing right here. The instruction of the problem says, of any of the problems here says, let's find the domain of the following function. Okay, so now I am going to look at the following one. And so, right from that demonstration example I did, how about f of x equals square root of 3 minus x. All right, square root of 3 minus x. Let's see what we do with that. So, just like that philosophy just like that fundamental I pointed out earlier. Now we have, in observing our function here, I'm seeing that there's a square root involved in our function. I'm not saying that the square root always have to be the only thing. No, it could be something else in there, but now just focus right on the square root right there. Then inside of the square root, we have a 3 minus x. That's what I meant by the expression inside the square root. Okay, and so in that way, this is what we need to ensure. And allow me to start using a brief term right here. We need to ensure that 3 minus x greater than or equal to 0. That's the number one, the priority that we need to ensure when you run into a square root. Okay, so now in order to ensure 3 minus x greater than 0, then it will produce some consequence. Ensuring that 3 minus x greater than or equal to 0, then we're going to have some direct consequence here. I'm going to subtract both sides by 3. This work here must be familiar, isn't it? But doesn't it? Okay, it's just the basic solving an inequality that you've learned from your previous course. Because right now what we have is an inequality, and then now we're going to solve for the x values that satisfy this inequality. Okay, so we're now looking at minus x to be greater than or equals -3. I am going to divide both sides by -1. But now anytime, be careful, anytime we're dividing or multiplying to an inequality a negative number. So here I'm dividing, then make sure that in the next step we're gonna flip the sign. Because right now I don't flip right now because I just want any students to learn that we can still divide and multiply. But now, since in the word of inequality, in the next step, it's going to have to result the inequality here being flipped, because it's just the way inequalities are. Dividing or multiplying a negative number to both sides will flip the direction of your inequality. So now in the next step, I'm producing, so minus x divided by -1 gives me positive x on the left hand side, positive 3 on the right hand side, but now it's less than or equal. X is less than or equals 3. Okay, so here's the thing. We found what we need. We needed to ensure 3 minus x greater than or equal to 0. And we found out the only way to satisfy, the only way to ensure 3 minus x greater than or equal to 0 is to pick x less than or equals 3. So anytime we pick x less than or equals to 3, it will work in this function. So now, see, quick demonstration. F of 3, x can equal to 3. So f of 3, let's find out. Square root of 3 minus 3 substituted in as the input. That means it gives me square root of 0, and that's equal to 0. It worked. Okay? And I'm just demonstrating, I'm just trying to explain a little further why, this is working. Okay? And that's what it means by satisfying 3 minus x greater than or equal to 0. And so f of, now let's pick a number less than 3. 2. Okay? For sure less than 3. That equals square root of 3 minus 2 in parentheses. Okay? That's square root of 1. That equals 1. That worked. Okay? So any other values continue to be further less than 3. Any value further less than 3, it's going to work. But now if we go with f of 4, okay, well, the inequality already said that if we use values less than or equal to 3, we will ensure this, and it will work for our function. If we brutally try 4, which is greater than 3, see, out of this, I mean already an exception of that, right? I mean already out of that rule right there, then let's see what's happening. 3 minus 4 gives me square root of -1, which is undefined. That's why this was an effective tool for us to know that, hey, which values we should choose to ensure this 3 minus x greater than or equal to 0, and to ensure our function has a defined answer. Okay, so now at this point right here, we are a lot closer. We already have a clear picture in mind about what our domain of the function is. Remember, possible inputs, okay? Possible input values. So what are the possible inputs values? X less than or equal to 3. Those are the possible input values. Okay, those are the possible input values. Okay, but hold it. That's not a widely accepted way to write your answer for a domain. So now let's try to bring that into interval notation. So we need x less than or equal to 3 to be in the domain. Draw the line of numbers again. 3 is somewhere. Okay, anywhere less than 3 according to the inequality. And then we take 3, accept 3. Okay, so that's our domain right here. So now, as a final answer, then we're looking at minus infinity to 3 right there, anywhere from minus infinity to 3. And we include x equals 3 in this case. That's our final answer for the domain, even though this was already the logical reasoning for where we should choose our domain right there. our domain is anywhere less than or equals 3. But now formally in interval notation, this is how we express our final answer. Okay. All right, so now let's look at another one. So now let's look at part B right here. All right, so part B now, let's look at our function f of x equals 3 minus square root of 6 minus 2x. Okay, so here's our function. So once again, now, so this function has even more things involved than the earlier part A right there. Okay, but once again, no worries. There's square root involved. There's square root involved. Focus right on that one. Because there's this 3 right here. It's not a square root, so nothing to be concerned, nothing much to be concerned about that. Tackle right on the square root right here. We need to ensure, when you see square root, then we need to ensure that 6 minus 2x greater than or equal to 0. Once again, because simply this square root of mine has the entire 6 minus 2x as an expression inside of it. Okay, so I just simply need to ensure that the whole 6 minus 2x greater than or equal to 0. Just like what I said, just like back to what I said earlier, the expression inside the square root needs to be greater than or equal to 0. We always need to ensure that. Okay, and so now to ensure 6 minus 2x greater than or equal to 0, we're now looking at this, we're now seeing this as an inequality. Okay, so to ensure that, we need to find out which x values will satisfy this inequality. Now we're solving for an inequality again for x. So subtracting 6 from both sides, okay, I'm going to end up minus 2x greater than or equal to negative 6. Okay, so right now the inequality reads minus 2x greater than or equal to 6. I am going to divide the negative 2 factor from both sides. So right now I just want to enforce that we at the current step we are going to divide negative 2 from both sides. But now when you arrive at the next step after dividing the negative 2, then make sure, it's just the way how inequalities are, make sure to reverse the direction of that. So now it says, it reads x is less than or equal to positive 3 again. Okay, so the way how it says, and at this time I'm not going to have to show the demonstration here anymore, but see, in order to ensure 6 minus 2x greater than or equal to 0, because that's the requirement for any expression inside the square root. In order to ensure that, we need x values less than or equals 3. Okay, so now in that way, all right, so we let to x less than or equal to 3. So that's our work, and you can also write this work out here. I'm short of space, so that's why I have to write the final answer. I mean the x minus less than or equal to 3 on that little space and erase this space of my board here. So now imagine that we know our goal right there. We need to be looking for x less than or equals 3. 3 is here on the line of numbers. Okay, we're taking any values less than that, and we're including 3. So now the answer comes clear for the domain here. As far as the domain of this function, we need anywhere from negative infinity to 3, and we're including 3. All right, so it happens to be the same answer with the earlier part, but there was no intention at all. Okay, it's just, and it doesn't always have to be like that, but the way how we solve is always, anytime we ending up with a square root, anytime we have a square root involved, we need to make sure that, we need to ensure that 6 minus the expression inside the square root should be greater than or equal to 0. Okay, so at this point, let's make a generality that combines from the two examples of 5 and 6 together like that. All right, so primarily for anyone, now I'm not saying that these are the only kinds of function that you are seeing, having a denominator or having a square root. I'm not saying that these are the only kinds, but at least at the time of your learning, when you're viewing this video lesson, you have only experienced those two kinds of function where some x values can cause troubles. Okay, and then later on, as you become more mature in your mathematical and in your mathematical experience, and it still exists right in this course we're learning, but as we move toward the closer end of the learning term right there, of the academic term, then you're gonna start seeing some other function where you're gonna need to consider the domain even more cautiously. Okay, but for now, let's come up with a couple of generality right here. Okay, if the function has a denominator okay, if the function has a denominator, then we just need to ensure that the denominator is always not equal to 0. And then from there, we're going to start looking for the bad guys and all that. So if we recall from example 5, in that case, the only way to ensure the denominator is non-zero, we're going to purposely set the denominator equals 0. And then we find the bad guys from there. But the main fundamental is to ensure denominator is not equal to 0. Okay, and then in another case, and there will be times where the two problems here all come together. We have functions that have both denominators and square roots as well, but now at least I'm tearing it down into two separate cases right here. So if the function, okay, if the function has a square root, okay, or now even more specifically, even root, okay, then this is what we do. We need to ensure the expression inside of roots, the whole expression inside of roots. We need to ensure that expression greater than or equal to 0. Now, I apologize a little bit for the lengthy wording right here, but I mean we need to ensure the expression inside of the roots to be greater than or equal to 0. And that's the generality, that anytime you run into either one of these two cases, and then in a worse situation, which I will, toward the end of this lecture right here, I will bring up some example problems, some challenges where some functions out there combined, some functions out there have both of these. It have denominators and it have square roots. Okay, and we're going to have to mix the two requirements here together. So these are the two main requirements that we need to focus to right now. We need to ensure denominator is always non-zero, not equal to 0. And we need to always ensure expression inside of a root to be greater than or equal to 0. Okay. All right, so now that I've made two highlights about some of the general requirements about some of those functions that we have commonly seen. So let's see how those highlights, those advices I've made on the other board can be useful into our own problem solving. So let's now look at another example. So let me take you into example number 7, where we can see how those highlights, those advices can be applied here. And so now in example 7, it is another example where we are focusing on finding the domain of a function. So let's now look at example 7. So let's find the domain. Okay, find the domain of the following function. Okay, So, and the idea now is that the wording might be a little shorter, or the instruction might be a little different, but it's just exactly the same kind of problem. I mean, exactly the same the instruction with the earlier example in example 6 like that. Okay, but now I'm gonna take you into a slightly more challenging kind of problem. So let's now look at part A right here, where I'm looking at how about a function f of x equals and define as the following rule over here. So square root of x plus 5, okay, divided by x minus 6. Okay, so square root of x plus 5 and divided by x minus 6. So this is where I was saying earlier that the two advices, the two highlights, the two general requirements are all applicable here. Okay, and the two advices I've pointed out are all useful and to be applicable in this particular problem. So why am I saying so? Because we have in this particular rule over here, we have some square roots involved. That's just right out of observation. And we have a denominator. This entire rule over here, this entire function has a denominator. Okay? And so in that way, in order to tackle down the problem, it's not only one requirement that we have to follow. It's not only this requirement about the square root that we have to follow, but we're going to have to blend in both of these two highlights, both of these two advices into the problem like that, because we do have denominator and we do have an expression being inside of a square root. We have square root involved. So anytime having a denominator, we have to ensure this, and anytime we have a square root, we have to ensure this. Okay, and then now in the worst case, like the problem I've already written down on the other board, and we have to ensure both. Okay, so now, all right, so we have square root. So there's square root, okay, and then there's a denominator, and that's what I meant earlier by we have to ensure both, because there's square root and there's the denominator. And square root, it doesn't even have to be specific about where the square root is located. In this problem, the square root is in the numerator, but that's not the issue of the problem. The issue is the square root itself, where we need to meet that requirement that I was stating in the other board right there. All right, so now there's no specific order about which requirements we have to maintain first. So we can just think about we have to ensure two separate works. So how about let me tackle down with that denominator first. And like I said, working on the denominator first or working with the expression inside the square root first, it's really not an important point right here. So now we're looking at the denominator, okay, and we don't even have to write down in the way how I'm writing like this. For anyone who is doing the work, you don't even have to write it down like this. But because I'm teaching, so I just really have to tear it down into a very careful step right here. So for the denominator, what we have is x minus 6. Okay, and maybe it would be a little better that I write it to the further left right here. We have to ensure that x minus 6 is other than 0. X minus 6 is other than 0. All right, so let's now throw in some scratch work. So x minus 6, we need to ensure x minus 6, that entire denominator, to be other than 0. So here's the consequence. So now the technique here again is saying that the method to ensure this is that we're going to start out by letting the entire denominator to equal 0. See, we purposely let it come to the case where it's being bad, and then we're going to search for who caused that bad situation. Okay, we're going to find that x value, that bad guy that caused the denominator that causes. It could be more than one guy. Okay, so we're looking for that bad guy or those bad guys that cause the denominator to equal 0. Okay, and so now solving that algebraically, by adding both sides, adding 6 to both sides, I'm looking at x equals 6. So now we have immediately found x equals 6 will cause this denominator to equal 0. So that means for the denominator, to satisfy this denominator, we have to ensure, again, we have to originally ensure x minus 6, the entire denominator, to be non-zero. Okay? But that leads to saying that we must ensure that x is other than 6, because we found a bad guy. This bad guy, again, just like that exact same philosophy, that exact same logical reasoning I've made earlier in example 6, that we search for the bad guy, but now once we've found the bad guy, we rule him out of the domain right there, okay? Because this bad guy causes the denominator to be 0, which is undefined. All right, so now one thing we found: x must be must be other than 6, not equal to 6. All right, so that we took care of. We took care of the requirements for the denominator. So now I'm going to move on. I'm going to move on to the square root expression. And like I said, right now in my work right here, currently I'm working with the denominator first and then the square roots, but really it does not really matter which one that we're starting out first. These are pretty much two independent works right there. Okay, so for square root, here's the only place where I see the square roots. Okay, now I'm not saying that this is the most challenging kind of problem, but as you build this fundamental over here, as you build these are solid building blocks right here, then your work later on, even outside of my own lecture, outside of my own examples that I deliver, okay, you should be able to build your own skills to handle, ready for you to handle the even more challenging kind of problems out there. Okay, so for square root, I'm looking at square root of x plus 5. So the expression inside of x plus 5, this is what we need to ensure here. We need to ensure x plus 5, the entire square root inside the expression. The inside the square root has to be greater than or equal to 0. This is what we need to ensure, because I am following exactly what that advice I've had right here. If the function has a square root, as long as you recognize the square root, we're going to take the entire expression inside the square root and ensure that that expression maintain a value, an overall value greater than or equal to 0. Okay, and so it comes straight out from the math, but here I'm writing that down as an advice for and as a guideline for anyone to stay align with that guideline right there. Okay, all right. So now in that way, in order to ensure x plus 5 greater than or equal to 0, now we have just now produced for ourselves an inequality to solve for. And here, simply subtracting 5 from both sides, I am going to produce x greater than or equals -5. So if we choose any value for x greater than or equals -5, then we are going to ensure that we should be able to ensure that this x plus 5 is greater than or equal to 0, and then it will fulfill the requirements for the square root expression. All right, so we have found two separate answers to fulfill our two separate requirements. But now we have to come up but that's not the total answer. That's not the overall answer to our domains. Okay, so the idea now logically says we need to ensure that x is other than 6, and also x has to be greater than or equal to -5. X is greater than or equal to -5. Okay, so we have to write a final answer. We have to write a domain that ensure both of these requirements are being in there. All right, so in that way, here's my next advice right here, and I've been finding this extremely useful right here. Draw the graph. The graph with the shading, anyone knows about this. Put the numbers on the line right here. And it never hurts to draw two graphs separately. Let's draw two graphs parallel with each other. Okay, this is my own style of doing this. When I was little, when I was young doing this work, I come up with this, and it keeps things organized. And the more organized we are, the better it is. The more organized I was, the better it is for the math work. So the two lines of number. This one here is for the denominator. So now let's say 6 is somewhere here. Okay, we want to be anywhere aside from 6. So that's one requirement. Okay, and then think about just the exact same line of numbers, but I'm just making a duplicated version of that. So negative 5 is somewhere out here. Okay, negative 5 is somewhere out here. And then I want anywhere including 5, and shade it to the right, because it's saying x is greater than or equal to negative 5. So it produces this graph. Whereas x is other than 6, this other requirement implies this shading right here. So now it's time that we logically combine the two requirements here together. We need to find all of those x values that satisfies both. We need to find those x values that satisfy both of these requirements. Okay, so now think about, you can either bring them into one and look for the double shading. Okay, so I should have done the shading for this graph here the other way around, so that it can. Okay, so I should have done the shading on this graph the other way around, so that now when we bringing the two graphs together, we can see the overlapping of the two. All right, so now bringing the two graphs together, we can see that, so these two regions, okay, will overlap. All right, and then that one here has to be ruled out right there. Okay, so now here's how it can all be put together. So now as a final answer, here's how I'm doing it. And then this is just extra and this is just optional over here, but you can think about if we put these two together, if we combine these two together in one line. I mean, for anyone who's mature enough in math and quick enough, you don't have to do this extra step, but it never hurts to do extra math work. Okay, so negative 5 is now here, 6 is here. Okay, we're ruling out 6 according to that result, but then we're still shading anywhere else outside of that, and we're including 5 right here. That's the idea. This is the combined version from these two separate requirements. All right, so now, see, and that was the double requirement right there, so I should have also done the double requirements. Okay, so now in the end, after seeing that final combined graph right here, then now I'm going to make my final conclusion for the domain of this function. One interval I have is from anywhere between negative 5 and 6, clearly. Okay, negative 5 and 6. And I will include negative 5, and I'm not going to include positive 6. So it's parentheses here and that. All right, and now, but outside of that interval where we have already decided the two ends right here, we also have another interval to the right-hand side of 6. So now it's 6 and above. So 6, comma, positive infinity. And always infinity comes with the parentheses. But 6, we don't want to include 6. So we're putting parentheses here. And now we put a union in these two disconnected intervals. So that's our final answer about the domain of this function. It has to be anywhere from negative 5 and above, but then we're excluding 6. That's another way of saying that. But you know, sadly, when we're writing it down in interval notation, we have to tear it down into two separate disconnected intervals. All right, so that's one problem for this kind right here. And now, since you're seeing where I'm going with that, right? Let's head ourselves into another problem in this particular class of problems right here, in this particular example 7. Okay, so now let's erase the space here. And things can now start picking up pace a little bit. All right, so now let's look at problem B right here. How about our function here? F of x is defined as x minus 3, okay, and divided by 4x plus 8. Okay, 4x plus 8. All right, so now here's how things work. Here's how things work. Do I see a square root? Yes, I spotted a square root. Okay. Do I see a denominator? The square root itself is also a denominator. The square root itself is also a denominator. Okay. So now, so that means out of the two advices, out of the two highlights about the key requirements here, that we about the, you know, as far as a checklist for what to ensure, we have to ensure both of these two. We need to ensure to have the denominator non-zero. We have to ensure the expression inside the root greater than or equal to 0. Okay, and so now I'm breaking this down into really elementary steps right here, but believe me, one day when you are mature enough in your mathematical skill right there, then you can start going a lot faster than me, and you will see things a much faster way. Okay, but right now allow me to really break it down and try to align with this guidelines right here. Okay, so now, just like how I was doing in part A, so how about this? Let me, usually the order doesn't matter, but let me handle the square root requirements first, because it's easier. I mean, and even if you're working independently and you're starting out with the denominator, it wouldn't hurt as, I mean, it wouldn't hurt as well. It wouldn't hurt either. So for now, square root, as far as ensuring the requirements for the square root to be fulfilled, all I need is, I just need to make sure that 4x plus 8 has to be greater than or equals 0. That's the one thing I need to ensure. Okay, so that means now let's do a little scratch work right here. 4x plus 8, or if legally you can also put this into your own written work if you have to. If your instructor, if I require anyone to do this kind of problem in the written, with the written steps. Okay, it's just in my, I could, if you decide, or if you are required to put this written work on your paper, then make sure this is a continuation of that. I put it here just simply because I'm out of space there. Okay, greater than or equal to 0. So 4x plus 8 greater than or equal to 0, and now that I've just produced for myself an inequality to solve for. So we need to look for x values that satisfy this requirement for x plus 8, the entire expression inside the root originally, to be greater than or equal to 0. So now I'm going to subtract 8 from both sides, the standard work to solve an inequality. Here I'm looking at 4x is needed to be greater than or equal to minus 8. And then further I'm going to divide both sides by 4. And that means now in my next step, and you have seen this a couple times already in my lecture here, and of course this is a known property that you should have had from your you should have learned from your prerequisite course right here. But see, dividing both sides or multiplying both sides of an inequality by a positive value will not change the direction. Will not change the direction of our inequality. Meaning, in the next step, 4 cancel with 4 leaves behind 4 canceling out with 4 leaves just x here. Greater than or equal. That's what I meant by not changing the direction of the inequality. And now minus 8 divided by 4 is negative 2. Okay, so now here's what I understand. I mean, here's how I'm seeing it. In order to ensure this, in order to ensure 4x plus 8 greater than or equal to 0, it leads the only satisfying x values are those x values greater than or equal to negative 2. Right? We need to ensure 4x plus 8 greater than or equal to 0. That leads to, we must ensure we choose x values. And now that starts ringing up a bell for us, about the domains right there. We have in the domain, at least what we know about the domain, the possible inputs is that it has to be greater than or equal to negative 2. All right, so that's one of it. Okay, so now let's look at the denominator. Okay, let's look at the denominator. So for the denominator, it is, we just want to ensure the entire denominator is going to be non-zero. Okay, so we just want to ensure the entire square root of 4x plus 8 to be other than 0. Okay, square root of 4x plus 8 should be other than 0. We take the entire square root expression, we take the entire denominator, and we want to ensure that whole value, that value of the entire expression is other than 0. And so now, once again, it's very similar to that logical reasoning I've made many times up to this point. to ensure this, we're going to start out by chasing or searching for the bad guys that cause, we're going to search for the bad x values, the bad guys that cause square root of 4x plus 8 to equal 0. This is what we're starting out. In order to ensure this, we start out by searching for this. Okay, and now searching for this. Now the equation itself all of a sudden brings us into a slightly challenging, a slightly not very familiar function, of slightly unfamiliar equation to somebody. But it's okay. It's easy enough to see that the only way for a square root expression to equal 0, the only way is that the expression inside. So it leads to, from here, or think about, we can square both sides of that. Okay, so square both sides of that. It will lead to 4x plus 8 equals 0. So again, ultimately the goal here is I'm trying to search for which values of x satisfy 4x plus 8 equals 0, because that's the only way where we will reach to square root expression equals 0. Okay, but now once we've let it here, then that's easy. Okay, we can solve that by simply subtract 8 from both sides and divide both sides by 4. I'm running out of space here, so I'm going a little loose in the steps right there. But that needs to be x equals -2. So when x equals -2, it will cause 4x plus 8 equals 0. And consequently, it will cause 4x plus 8 in square root equals 0. Now, putting the square here was just a technique. But in case you have not learned about that technique, in case you haven't learned that technique, you can just think about the only way for a square root expression to equal 0 is that the inside expression has to equal 0. And we take things from there. Okay, and we take things and solve it from there. And that's why it's equivalent to squaring both sides. Okay, all right, so now, but this is the bad guy. So much explanation for the solving work, but in the end what we have found here is the bad guy. All right, so now I have to take this out because that's just the solving work. When you are doing your own written work and you have more paper space like that, then you're very welcome to leave those works there, because the more steps you show, the better documentation it is. But now, for the domain, we need x to be other than -2. So we have another requirement. All right, we need x to be other than -2, because from what we've solved earlier, x equals -2 will make square root of 4x plus 8 equals 0. But now we want square root of 4x plus 8 to be not equal to 0, to be non-equal 0. And so in that way, x has to be other than -2. All right, so you feel free to take a moment to pause the video and think of what I was saying. In order to ensure square root of 4x plus 8 to be other than 0, we have to ensure x is other than -2. And the work was done previously, and that I had already erased. So now it's time to combine the two requirements here together. We have found the two requirements that we need in order to fulfill the key requirements here. So now, from where it says right here, let's draw two line of numbers. Okay, they both have 2 in it. For the square root one that we started out first, this is -2, and this is -2, the exact same place. Okay, for the first one, we can just take anywhere including -2 and above, because we want it to be greater than or equal. Okay, and then for the second requirement, we will take, and now I'm going to draw the shading the other way around. So we're going to take, for this denominator satisfaction, we take anywhere else other than -2, and we're excluding -2. We're excluding the -2, and so now I brought in that idea about combining the two charts here together, the two graphs here together, and this now I'm forced to erase away the two works here. So now combining these two together, we can ultimately come to the following. So now combining the two together, -2 is here, but so we don't want -2. We don't want -2 because of that. Okay, if we're including it, it's going to run into this. So the better one is to take away this. That's more like a combined version. And then now see the double shaded region is here. The reason we don't take the other shaded region because it's only satisfy one requirement but does not satisfy the other one. So now the only part that satisfy both, it's the double shaded region. So now from reading this final graph, now we're clear with our answer about the domain. Okay, so the domain here is anywhere between -2 and infinity. Okay, and of course it's always parentheses on the infinity side, and it's here it has to be that parentheses on -2 because we're not including -2 here. All right, and so that's the answer of the domain of this function in this interval notation. All right, and so that's how we tackle down and that's how we blended the two requirements together. Okay, so I'm going to bring in another problem which is slightly more complicated, and these I introduced in the examples are commonly seen enough, but I'm not saying that these I'm teaching here are all the challenging problems out there. I mean, there are still, those problems where you find domains of a function a lot more challenging than these, but those are kinds of problems. Those problems are not very applicable, not very practical to be introduced in a classroom setting right there. Okay, and it takes patience. So once you build a strong foundation from these examples I'm pointing out, then you should be able to spend your own time and explore your own patience to work on those more challenging problems right there. But allow me to not introduce those more challenging problems because it is nearly impossible that any instructor will be able to show all examples out there. All problems, all challenging problems out there, because there will always be more problems coming out every day. Okay, all right, so now let's look at a third problem right here in this example 7, and we can call this the last one for this particular example. Okay, so now let's look at part C right here. So how about I'm defining my function to be 1 over, and now I have x plus 2. Okay, and then a square root of 4x plus 1. All right, so now I have that. So 1 over x plus 2 times square root of 4x plus 1. Okay, so now in that way, again, here's the thing I have spotted. I have spotted a square root right there. Okay. And I have spotted a denominator, and this denominator is even more complicated than the earlier denominator we have seen right there. Okay, so now let's see how we can tackle this down. So I'm going to start out with the square root first because it's simpler. It looks clearly simpler in this overall problem right here. So now for the square root right here, this is the only square root we have. Square root of, and the inside expression here is a 4x plus 1. So for that square root, as far as that square root, we need to ensure 4x plus 1 to be greater than or equal 0. Okay, so that's what we need to ensure right there. All right, so now let's spend some time working out to find out which x values, what domain of x values, right? What zone of x values will satisfy this requirement. Okay, so to ensure 4x plus 1 greater than or equal to 0, then I'm going to need to subtract -1 from both sides, because now we are solving. In order to find the x value satisfying this inequality, we are going to solve that inequality for x. Okay, so subtracting 1 from both sides, I'm ending up with 4x greater than or equal to -1. And then I am going to divide both sides by 4. And then since the number we're dividing on both sides here is a positive number, we don't need to flip the inequality. So now it's going to be just x greater than or equal to -1/4. Okay, so x equals greater than or equal to -1/4. So that is the requirements. In order to ensure 4x plus 1 greater than or equals 0, then it leads to we need to look only we only use inputs that's greater than or equal to -1/4. That's one requirement fulfilled. All right, so now let's move on to the other requirements about the denominator. All right, and I need the viewers, I need my students who viewing this lesson to follow with this. Next one here, as closely as possible, pay all of your attention here. So now the denominator, I need the denominator. I need to ensure the entire denominator. So the entire denominator, sadly, is a product of an x plus 2 as a factor times with the square root of a 4x plus 1. I need the entire denominator here to be non-zero. I need the entire denominator to be non-zero. Okay? So just like that exact same logical reasoning I pointed out earlier, in order to ensure the entire denominator here to be non-zero, then that means so now as a solving work, that means x plus 2 times in product with square root of 4x plus 1. That means this equation has to be, this entire denominator has to equal 0. We first purposely set the entire denominator equal to 0. We want to find all the bad x values that cause this entire denominator to equal 0. Okay, and so now I'm going to take the space on my other board, and whatever I had on the other board, I'm now going to need to erase that and make more space for myself to write this down. Okay. All right, so now let's observe this equation. So here we're actually producing an equation that at first it looks a little challenging for this equation. Well, ultimately as a goal, we want to look for an x value or any of the x values that cause, so there could be more than one x values that cause this entire denominator to equal 0. And once we have found all of those, we're going to rule them out from the domain right there. Okay, but then the challenge is, how do we solve something like this? Okay, so at this point in your pre-calculus learning, you might have seen or you might have not seen, so I'm not too worried about any specific method to solve this, but one thing I'm sure anyone must have seen. It's a product. So the only way for a product to equal 0 is that we can set each factor here, the x plus 2, as one separate factor. We can set that equal to 0. And we can tear down the other factor. So the entire square root of 4x plus 1 can also be set equal to 0. Now we produce for ourselves two sub-equations. And we can solve these two independently right here. Okay, and whichever values that satisfy this equals 0, or whichever x value that satisfies this, the x plus 2 equals 0, any one of these two will cause the whole product here equal to 0. Okay, so you have seen that particular technique before, that anytime you have a product, okay, a product of a times b equals 0, then we can always have a equals 0 or b equals 0. Okay, that's one algebraic property that we have seen quite a few times in your prerequisite course right there. And so surprisingly, that property you've learned also applies here, where this is a product of two, a little bit scary looking, that a factor being just a linear factor and then the other factor is a square root. Okay, but now when we step a little forward and really just apply that fundamental we have learned into this, we produce two sub-equations for ourselves. Okay, so on this one here, it's easy. Subtracting 2 from both sides, and that leaves x equals -2. So that tells the story for one of them. If x equals -2, this entire product will equal 0. So we have already found one of the bad guys. Okay, one of the bad guys out there has been found. Okay, so now what about the other one? But now when it comes to this, then we have seen that similar to the earlier the example problem I brought up right here, the only way for a square root to equal 0, you can argue that the only way for a square root to equal to 0 is that its inside expression must equal 0. If you try to stay away from knowing too much techniques, you can keep that logical thinking. the only way for a square root to equal 0 is that the only way is that the inside expression has to equal 0. Okay, so I'm showing this logic so that in case you don't remember much about the technique to handle solving an equation with square root, then we can disregard about technique. Just when it comes to this simple case, a square root equals 0, the only way for that square root to equal 0 is that the expression inside has to equal 0. Okay, and then from here it takes us back to the simpler kind of equation, subtracting 1 from both sides. Okay, and here we're looking at 4x equals -1, and we can divide both sides by 4, and it's an equation, ladies and gentlemen. Okay, so here we have found another bad guy, equals -1/4. Okay, so this bad guy, why is it bad? Because it causes this entire square root expression factor to equal 0. So consequently, the whole product here, which is our current denominator of the problem, will equal 0. That's the logic and the reasoning of that. Okay, and so now we've found we have at this point spotted two bad guys that cause the denominator to equal 0. Okay, so now I'm gonna list them here. So as far as the denominator, we need to ensure the denominator to be non-zero, but we have spotted that the only way to ensure this to be non-zero, we have to exclude -2, because we spotted that -2, x equals -2 is a bad guy, and we also spotted that x equals a -1/4 is also a bad guy, so we need to exclude out -1/4. So we have two values to exclude because those are the bad guys. They cause the denominator equals 0. All right, so now once I've tear it down, okay, once I've really torn it down, then let's put everything together. Okay, so now, again, I'm going to use this space and allow me a minute to erase it. Okay, so for the square roots, okay, that requirement there says negative, okay, -1/4 is about here. So this is for the square roots. Okay, so for the square root requirements, graphically we can draw, we do include -1/4, and we take anywhere above that. This is what it said earlier. X is greater than or equal to -1/4. So -1/4 is somewhere here. Okay, and just like that. All right, this is just what happens right there. I was just graphing that solution of this inequality. Okay, and now for the denominator. Okay, for the denominator, I made this the exact same. Think about the exact same line of values. Okay, line of numbers. And now I'm going to think about, and it's really meant to have the exact same scaling and all that. Okay, so -1/4 is also here. Okay, and then -2 is here. And then we have spotted that these two guys are here on this line. The -2 and the -1/4 are all bad for the denominator, both of these. And so for the denominator, then we want to be anywhere away from -2 and -1/4. So I'm making that shading outside of those two, excluding those two values. Okay, and so now it's time to combine and blend the two graphs together and look for the double shaded region, as well as see how these requirements blend together. So now as we blend it together, then the final graph comes as following. Okay, there's a -1/4 right here. Okay, there's a -1/4. The double region, the double shading goes here. Okay, that's the double shading. Okay, and then now one solid, the same -1/4, but on one graph takes the solid point, and on the other graph takes the empty point. So now in the combined version, we have to take the empty point. And then here's the double region. Here is only a single shaded region right there. So the entire area here is disregarded. Okay, so now that comes to our final solution. Okay, so now that means after looking at that graph, that means our final domain here. All right, so as far as the final domain, by seeing that from the graph that we have seen earlier, then now it's going to be anywhere between negative 1/4 and positive infinity. Okay, and of course it's always parentheses on the positive infinity, but it's also parentheses on the negative 1/4 because we excluded that. All right, so that's the domain of this particular function. Okay, because think about it. I mean, why not any value? Why not any values between negative 2 and 1/4? Because see, if we take a value here between negative 2 and 1/4, it satisfies the denominator to be non-zero, but it fails satisfying the square root. It doesn't work for the square root, so it also doesn't work. So we remember we have to find the overall solution that combines the two requirements here together. That's why we only look for the double shaded region. And then if a solid point comes at the same point, but on one graph it's solid and on the other graph it's empty point, and together it has to be an empty point like that. All right, and so that's how we tackle down this kind of problem, and came to that conclusion that this function has this interval here as the domain. Okay? Only x values in this interval satisfies only an x value in this interval satisfies this function to be defined. All right, and so that's all for this example 7, and it brings up those kind of problems where it's a little challenging and where we have to combine the two requirements, and we find the domain of a function where it has a specific rule written down right there, a formula, a rule, okay, an expression already written down. All right, but I'm not saying that these 3 problems that I brought in cover all challenging problems out there, but at least once you have seen through these and work through these problems right here, you should have built you can build enough foundation so that, you know, in case you see other more challenging problems, you can spend more of your time and be a little more patient to go through and use all of that tips and tricks I pointed out to solve those other challenging problems out there. Okay.